So we've seen one form of games, the normal form. Let's now move to the second very common form, and that is the extensive form. The extensive form comes in two flavors, a special case called games of perfect information and the more general case, games of imperfect information. We'll start with a simple form of games of perfect information, and perhaps the best way to start is through an example, starting with our familiar Battle of the Sexes games. So we have two spouses wishing to go together to a movie, but having opposite preferences. The one prefers to go to Pride and Prejudice, and the other Lord of the Rings. And here are the payoffs written. But now what happens if one of them gets to make their choice first, announce it, and only then the second player gets to make their choice? Well, a natural way to represent it is in the following way. Player one gets to move first, make their choice, and once they do, for example, they decided to go to Pride and Prejudice and announce their choice, player two gets to make their choice. And presumably in that case, they would prefer also to go to the same movie because their payoff is higher. This is very familiar. It's a game tree. It turns out that just to specify it mathematically is a lot of notation, and we'll go through it now together. There are also some notationally subtle issues that come up, and we'll point those out also. So let's start. We first need to define what a game tree is. We'll then need to associate players with nodes and to specify the payoffs. Most of that will be very straightforward, although notationally somewhat cumbersome. But as I said, there'll be one or two subtle things, and I'll point them out. Let's start with the game tree. Again, a very obvious concept of nodes and of a root node that's pointing to all others, and terminal nodes that point at no other. To specify that formally, we need to first define what a graph is. Well, a graph is a pair of nodes and edges are sets of edge is a pair of nodes. We'll assume that there are no self-edges with a node pointing to itself, but certainly you can have two different nodes pointing at each other. That would be a cycle. There could be a larger cycle of a larger set of nodes forming a cycle. A path between two nodes is simply a set of nodes starting with the first and ending with the other, such that every two consecutive nodes in the path there form an edge in the graph. That's a general graph. A tree then is a special case where there is some specialized node x0 called the root, and there is not only a path from that node to every other node, but there's a unique path. So there are no cycles in a tree. When we have such a tree, then that naturally defines this relationship of precedence, which is an ordering, but a partial ordering. So one node precedes the other if it is on the path between the root node and the second node. And of course, there could be two nodes, neither of which precedes the other. Finally, we define the set of terminal nodes Z to be a subset of the nodes such that there is no node that they precede in the tree. We now know what trees are. The next thing is to associate players with nodes. That's very straightforward and also notationally not complicated. We simply have a function, an assignment function, that maps every non-terminal node into the player in that node. And we're assuming here that the players are represented by the natural numbers. The next thing is to say what players can do. So we need to specify the set of actions. So, for example, say that at this node, the two actions available are choosing Pride and Prejudice or Lord of the Rings. And so for that, we need to specify the actions available, and it better be the case that each action takes you to some successor node. So we first define the set of successor nodes to be all the nodes that follow directly from a given node. In other words, nodes that this nodes precede, and there's no node intervening between the two. And it better be the case that each action leads to one such successor node, and each successor node is led to by one action. Now that we know what agents can do, we just need to say what agent care about, and then we'll finish defining the game tree, and we simply need to associate some payoffs, saying that 1 is the payoff to agent 1, say, and 2 is the payoff to agent 2. So let's do that. We'll have simply a payoff function from the terminal nodes to the real numbers. One payoff for each agent. So that was a lot of notation to specify the obvious. Here are a couple of things that are not completely obvious. What are the strategies in such a game? We'll start with pure strategies, and pure strategies are simply a specification of what to do at each node. That is, for each agent and each node that belongs to that agent, we'd better specify one of the available actions at that node. There's a note here, and this is one of the subtle things, that we need to specify what to do in every node, also so-called off-path nodes. Let me illustrate this. Here's the first example, very straightforward, our battle of the sexes with sequential moves, and you can see that player 1 has 2 pure strategies, go here or go here, whereas player 2 has 4 strategies. For example, it can say, if I find myself here, I'll go here. If I find myself here, I'll go here, but if I find myself here, I'll go here, the blue strategy. You could also have a different strategy. If I find myself here, then I'll go here. And finally, it might say, if I find myself here, I'll go here, and similarly here. So 4 strategies denoted by these 4 colors. So far, so good, but now let's look at this game. Player 1, and never mind what this game represents, I haven't even written down the payoffs. I just want to see what the strategies available are to the agents here. So to player 2, there's nothing surprising happening here. It needs to specify what to do at this node and at this node. And this is a very pretty color. Maybe I'll use it more in the future. Player 1, though, what are its available strategies? You might think that it has only 3 strategies. It can say, I'll go here and then go here, or I'll go here and then I'll go here, or you might say the final choice is I'll go here. And those are the only decisions I can make. But, and it turns out to be very important from the technical point of view, when you have decided to take the green route, you also have to decide what you would have done had you found yourself in node 1. For example, do this. And that's a different strategy from the strategy of going here and saying that you would have gone down this path. And so player 1 has 4 strategies in this game. This is the first subtle point to make. And we call this an off-path choice because clearly when you have chosen to go down this cyan path, the choice at this node doesn't matter because you'll never find yourself there. But it turns out to be very important for the analysis of the game to see what you would have done had you found yourself in that position. Those are the pure strategies, and now we're going to complicate them. And the first way to complicate them, these two alternative ways, is the first way is to look at mixed strategies, and those are conceptually identical to the mixed strategies in the normal form game. We have pure strategies, and we're taking some probability distribution over them. That's all there is to a mixed strategy. But it's important to realize that the interpretation of mixed strategies is of randomizing in advance. So let's look at this, our familiar sequential battle of the sexes games as an example. We've already seen that player 2 has here 2 available strategies. We've already seen that player 2 has 4 available strategies. For example, this one, and this one, and the 4 other ones. Now, a mixed strategy means taking these pure strategies in their entirety and randomizing between them. So for example, saying I'll do the red strategy with probability 1/3 and the blue strategy with probability 2/3. That's a mixed strategy. But contrast this with what is a behavioral strategy. A behavioral strategy doesn't take the entire mixed strategy and then randomize among them, but it says independently, when I find myself at my node, let me randomize at that node. And so when I find myself at node X, I will, for example, let's look at an example here. So player 2 again says, at this node over here, I'm going to take this, I'm going to Pride and Prejudice with some probability, maybe 1/3, and to Battle of Sexes with probability 2/3. And that's a very different worldview, when I can, if you wish, in real time, decide how to randomize. So we have mixed strategies and behavioral strategies, and you might ask yourself, so does it matter? And the answer is no, it doesn't. At least it doesn't in these class of extensive form games of perfect information. And there's a theorem to that effect due to Harold Kuhn, and in fact, it's even more general than applying to the class of games of perfect information. But it's not true for all games, and this is just a heads up. When we define games of imperfect information, we'll come back to this issue. But for games of perfect information, the class of games with mixed strategies are identical to the class of games with behavioral strategies.